Welcome to another episode of the Evoke cast. I'm your host, Scott Johnston. With me today, I have Evoke coach Leif Godberson. Leif and I often have conversations where we get pretty far down in the weeds about training theory and kicking ideas back and forth. And I thought that this particular conversation today warranted another viewpoint and another voice. We've done a fair bit lately on Zone 2 training, including both a podcast and a pretty in-depth article. But I wanted to talk about the entire zone system, zone intensity, using intensity zones for controlling your training. But we're going to do it in a slightly different way today. And that is we're going to relate this to what's actually going on in the muscles, rather than exclusively stopping at the heart rate level. We're still going to be using heart rate as our metric for monitoring what zone you're in and how to control that stuff. But we want to peel the onion down one layer deeper and look at the, what's actually going on in the muscle. So thanks for joining me, Leif.
Nice to be here, Scott.
Yeah, so Leif's going to chime in whenever he sees me going too far down a rabbit hole or getting off track or that sort of thing today. So the first thing we want to talk about really is the training effect. These bullet points, I'm not going to read every single one of them, but I think so you'll be able to read them. But the reason we use zones essentially is so that we can control the intensity, because different intensities have different training effects. That's kind of the point of this slide. And if you don't have some sort of control or way of measuring what the intensity that you're training at is for endurance training, all this is going to be related to endurance training. Let me preface the whole conversation that, we're not going to be talking about really strength training at all here. Even probably we might not even touch on muscular endurance training today. But with endurance training, it is important to have some idea of what the training effect is and you can get that by knowing what intensity zone you're in. So we think that it's pretty important to understand training zones, just because, as I said earlier, not all these intensities have the same training effect. And if there was just one ideal intensity that we could all train at and do all of our training at, then we wouldn't need these zones. And in fact, that idea has actually been floated a number of times. I think it's pretty well debunked now, but there's a lot of people who I think still, even if they don't say it publicly, will essentially have many athletes train at their endurance limit, basically meaning that, if they've got a 45 minutes to go for a run before they have to pick the kids up at soccer practice, they just go run as hard as they can for 45 minutes. If they've got 2 hours to go run, then they run 2 hours as hard as they can for 2 hours. And obviously that's, maybe not obviously to everyone, but it ends up that's not a particularly effective way to train. In fact, it can be, it's what we often call death by threshold, of training right at one's endurance limit. And I think that, in my experience, I postulate that comes from the strength training world. And that is that when you do strength training, in general, if you want to get stronger, you need to train kind of at your limits of strength. Otherwise, you're not going to increase the strength of those muscles. And I think people take that same idea and try to apply it to endurance, where they train right at the limit of what they can manage and expect that to improve their overall endurance. But endurance, the qualities that make up endurance are so different, and they're quite complex. Remember, one of the things we've said often is that endurance is a metabolic effect, and strength is a neurologic effect. And you can't expect to train the metabolism the same way you train the nervous system. Obviously, that's a rather gross generalization, but I think people get the idea that, endurance is all about being able to metabolize fuel and produce energy with it. And that's not the case with strength training. So if we can identify these intensities and understand what's going on down at the cell, more at the cellular level, we believe very strongly that will help people optimize their training. Now, not everybody's going to need to go down even this rabbit hole that Leif and I are going to dive into today. You can still just stick with the old heart rate zones and you'll be just fine. But I think for people that are curious, going to this next level may actually be helpful for folks.
And Scott, I think perhaps, to clarify, we could, preface as saying that this is geared towards training and not sporadic exercise, and the importance of, quantifying the zones becomes more important as the volume and the intensity starts to go up.
That's a great point. Yeah, because we are, in general, we work with people who are involved in a training program. And how would you define the difference between training and exercise?
Well, I think to some degree, training has to be quantifiable, and it has to have, some sort of not necessarily an endpoint, but it has to have some sort of logical progression behind it, some structure. And I think that's the large differentiating factor between random exercise and training, is that training has a clear-cut purpose. The purpose can be a spectrum of things, but you have to have some rationale as to why you're doing what you're doing, which is important. If it's just exercise, which is completely fine, you're more so just going out to move, and that's fine, but it's not to any clear endpoint.
Yeah, and I think that the reason athletes engage in training is that they often, especially competitive athletes, have a singular goal at the end of their training progression, and they're training to enhance their performance at whatever this goal event is. Whereas for many people, random exercise is perfectly good. They just want to be active and stay healthy, and there's nothing wrong with that. And so, but even for the random exerciser, I think it can be helpful to understand, what the effect of different training intensities is, so that every time you go out the door, you aren't just, training, going as hard as you possibly can. But I think the reason we want to relate this to what's going on in the muscles and not just stop at the heart rate level is that we want to talk about how the muscle, what the action inside the muscle affects the heart rate. And I think as we progress through this, people will begin to see that. All these endurance sports are sports of locomotion. In other words, moving yourself from one place to another and working against some kind of external forces. Gravity being kind of the universal one for especially for mountain athletes, going uphill. And the way we locomote is by producing muscle force that causes our joints to go through different range of motion angles. And that force production comes from muscle contractions, and those muscle contractions are a product of the actual muscle fibers. And that's sort of that's the little rabbit hole we're going to end up going down today, is talking about the slow twitch, fast twitch kind of model for understanding muscle fibers and their force production. The slow twitch are really kind of the endurance fibers. These are the ones that propel you for hours upon hours. And the faster twitch fibers, which tend to be the higher force fibers, are ones that are going to be using for obviously higher speeds when you need to produce higher forces. And again, we'll be getting into more of that as we go along and how those things are separated.
And I just, one thing on this slide I think is particularly relevant is highlighting, locomotion is important in endurance sport. And at the end of the day, we have these two lactate turn points that we may use as our anchor points in the zone model. But at the end of the day, the goal is to get faster, and they're useful metrics, but that's how we really want to be, what we want to be working towards is, in fact, improving the actual speed of the athlete.
Yeah, I would say almost without exception, we, the coaches here at Evoke, we kind of downplay, let's say, laboratory testing. When we've got an option between a laboratory test and a performance test, an actual measure of how fast you can move for how long a distance, we'll always go towards the performance test, what we might call a field test, because in the end, that's what we're trying to improve. Many people will want to, one of probably the most common and I believe most over and misused test is for people to go into a laboratory and measure their VO2 max or max VO2, however you want to say it. It's the maximum aerobic power that they're capable of producing. And that I've talked about this a lot and I've got written articles about it, but I think it is nice. It's like measuring the horsepower in your car, and oh, I've got a 500 horsepower car. That's a pretty big, powerful car. But in this case, turns out that max VO2 or VO2 max, again, it's said in both ways, is not a particularly great predictor of performance. It's of the three primary endurance predictors, it's the worst of the three. The other two being your speed at the upper threshold, what we call the anaerobic threshold, and then the second predictor is the energy cost to move, or what they call the economy. Those two are much better predictors, but VO2 max seems to be the one that people like to use in laboratories. But we would rather just have somebody perform, a performance test, and are they faster now than they were 2 months ago? So thanks for bringing that up, Leif. I think that's a really good point.
Mm-hmm. Yeah, I think the example of the two marathon runners, if you have one who has a VO2 max of 75 and one who has one of 85, if the one who's at 75 is able to run has a threshold closer to their VO2 max, they may actually be faster than the person with the higher VO2 max.
Yeah, we often actually see that in among the elite runners, or even other lead endurance athletes, max VO2 correlates with performance pretty poorly. Like, the R squared is somewhere in the 0.4, 0.5 range. It's not a good predictor. You see often because VO2 max of 75 may be extremely economical at race pace. And so he doesn't need to use very much of that 75 milliliters per minute of oxygen. Whereas the person who has the 85, they might need to use almost all of that 85 milliliters per minute to maintain their race pace. And so they're not going to be very economical. They're going to be burning a lot more energy to stay at that pace. And as a consequence, typically they won't, if you have low economy, usually you're going to have poor endurance as well, or less endurance than someone else who has high economy. So, we've talked a lot about this already, I guess, why we think it's important to understand these. Normally we always define, always, I'd say we pretty much always define intensity in terms, and the zones in terms of heart rate, because it's very convenient, with these modern heart rate monitors that you can wear on your wrist. You can see very accurately in real time what your heart rate is. And while it's not a perfect proxy for intensity, it's plenty good enough for what we do. And there'll be cases where it isn't great, and we can talk about that, especially with when there's a very high muscle load, like in a muscular endurance training session, where heart rate, probably the correlation between heart rate and intensity begins to break down.
Yeah, I think just worth pointing out is this is one of the areas, particularly like in something like cycling, where the use of something like power is good because it is better at quantifying something with a like interval training, where the heart rate, because of it's just going to have some lag as it adjusts to the increased load, isn't going to be the best predictor. But with sports like running, trail running in particular, it's very difficult to have a really good, and it's less accessible to train with things like power. And once again, it comes back to using heart rate as a proxy works very well.
Yeah, and some of you may remember that I did a podcast about power meters last year, and it's probably worth going back and listening to that if you're into using power meters. I mean, I think it may end up being the wave of the future as they get better and better. I think they're already quite good. My problem with them is that they're so good that they give sort of this instantaneous power reading that will have a very erratic, it's going to vary from second to second, and it makes it kind of hard to look at your watch and tell what the power is. So you need to have some sort of be able to apply a smoothing function. And I think the power meters will do that. They will allow you to average it over, let's say, the last 5 seconds or 10 seconds. So they are a viable method of measuring this. It's just that maybe it's just because we're kind of old school and we've been using heart rate for so many years. That's sort of where we end up. And it works well enough, I would say. So the first step in understanding muscle fibers is to think about, how they're identified. It turns out that different muscle fibers or your muscles are made up of different types of fibers. And typically they've been categorized as 3 discrete types: the slow twitch, and then they're either called fast twitch A and fast twitch B, or fast twitch A and fast twitch X. Or sometimes this is called type 1. Slow twitch are called type 1, and sometimes a fast twitch are called type 2, 2A and 2X. The nomenclature in a lot of this exercise physiology stuff is a little confusing. So you have to be able to read and translate it. But we're going to stick with the fast and slow twitch idea or names. But this is sort of in general how they have been identified. Like if you went and picked up an exercise physiology text, you would see muscle fibers identified roughly like this, and in these 3 fairly discrete types, which we're going to talk about why we don't really think that's a great model, but that's been historically how it's done. And the slow twitch fibers are the ones that are the lower force. So these are the fibers that are, well, they do a lot of other things in our bodies, but we're going to just talk about the ones that help you move. So these are the fibers that have the highest endurance. And that's because they have a lot of mitochondria in them. So they have a capability of producing energy with aerobic metabolism. They have they're surrounded by the capillary beds that are very dense. So the oxygen doesn't have very far to move to get from the blood into the mitochondria. And they're pretty flexible in terms of the fuels that they can use, fat being one of their preferential fuels. They can also use glucose. And we'll get more into this, the part that we've highlighted there in yellow, that they also really like to use lactate as fuel. And the reason that's important is that in the fast twitch fibers, they almost exclusively use glucose for fuel, and one of the inevitable byproducts of glycolytic metabolism, the use of the breakdown of sugars for fuel, is the production of lactate. And it's kind of handy, and we'll talk about how this works later. I went into some depth on this in the Zone 2 article, but it's handy that these fast twitch fibers are producing lactate, and the slow twitch fibers can take it up and make some beneficial use of it so it doesn't accumulate, because there are some downsides to the accumulation of lactate in the muscle fibers. Anything you want to add to that, Leif?
I think just making note that, the slow twitch fibers in particular can use protein as fuel, but in the context of endurance sports, as we're discussing, it's negligible. So that's why we're largely just going to focus on fat and glucose.
Yeah, it can be complicated. I mean, actually, I had someone write in recently on the forum, and who wanted to have a much more in-depth discussion of physiology that I think is needed or is really appropriate for us to get a handle on, how to train more effectively. And this is one of those cases actually that we can sort of disregard the use of protein as a fuel when it comes to, sports activities. It's
Yeah, and
not.
if you're going down that path where you're preferentially using protein as fuel, then you've got some other issues to worry about.
Yeah, I mean, when you're using, like if you're in a highly ketogenic state, just as a quick rabbit hole, highly, very ketogenic state. In other words, you're really, relying very heavily on fat and the process of ketosis for producing energy. You'll also be burning fat, glucose, excuse me, so burning protein during that time, which is one of the reasons that I think athletes involved in a heavy training load, ketogenic diets are not very helpful, not very useful at all for them. I think that where ketogenic diets the reason they've become popular is for people that are training a very low volume but would like to lose some body fat, then they can be beneficial. But an athlete that's trying to carry a fairly heavy training load, I think that you end up with a lot of muscle wasting by using ketogenic diets because of that, and the high energy demands that are hard to meet with just the fat. Okay.
Yeah, and I think just the final thing that I think on that note is especially endurance training with the high volume of training that you're doing, which is in contrast with something like rock climbing, where you're just simply not doing the huge volume of aerobic training, which is a big differentiator in fueling.
Yeah, a good point. And very high energy expenditure in a high volume endurance training program. So this is the way these muscle fibers are often presented in textbooks and in literature, is that these slow twitch fibers, they look red actually under microscope because they have a higher, what's called a myoglobin content. And so they used to be called red fibers versus white fibers, which don't have much myoglobin or mitochondria and tend to be lighter colored. The slow twitch fibers are going to be the multi-hour type fibers, especially. So you can see we've got a middle distance runner and a sprinter, where the sprinter is going to be, or a sprinter athlete will typically have a very high percentage of the white fiber, the fast twitch fibers, and as compared to the slow twitch, the long distance runner. It's also, here's another way that these things are presented, and this is in the way these muscle fibers are recruited. We've got, again, very discrete categories here: slow, fast twitch A, fast twitch B. The slow twitch fibers tend to have, they're smaller in cross section, which is sort of what we try to represent with that drawing underneath each one of the runners, and they're also innervated by a smaller motor nerve, and it takes less nervous energy. I'm not going to go talk about how that happens, but it takes less nervous energy to fire the slow twitch fibers than it does the fast twitch fibers. And so these fibers are recruited according to what's called the size principle, so that when you begin to exercise, the first fibers that the brain begins to recruit are the least powerful, the slow twitch fibers. But then as the if the demands are high enough that the slow twitch fibers can't produce enough force, then it begins to recruit these faster or higher force fibers like the fast twitch A and then eventually the fast twitch B if very high powers are needed. We talked a little bit earlier, the slow twitch fibers have a lot of endurance because they rely on oxygen. They rely on the aerobic metabolism, whereas when you get all the way to the other end of the scale, where these highest force fibers, they're purely relying on glycolytic metabolism. Oxygen need not be involved in that at all. But again, we've just mentioned that when you have a lot of glycolytic metabolism, you're bound to have lactate buildup, which would, if you think about that you take that to its natural end point. This is why you can't sprint forever, because as the lactate accumulates, the glycolytic process begins to slow down as the glycolysis that's powering the sprint begins to slow down as lactate accumulates. We've all experienced this sensation to some extent. I mean, you can feel it real time. Just go out and sprint up a hill as hard as you can for as long as you can, and you will find that you will eventually have to stop. It doesn't matter how much willpower you have. If you had enough willpower, you could sprint to the point where you would literally fall over, because those muscle fibers that were propelling you, they stop being able to propel you, and you'd be slowed to a walk or a crawl eventually.
And I think the only thing I would maybe on this slide is just highlighting again, like we've broken the fiber model up into these discrete fiber types, but there's these hybrid fiber types that exist on the spectrum, like these hybrid fibers of, fast twitch A and B. That's in reality, they're not perfectly arranged to be slow twitch and fast twitch A and B.
Yeah, I think that there's been more and more research, and I think that shows that these muscle fibers actually exist along a continuum from the least forceful slow twitch fibers on one end of this spectrum to the most forceful fast twitch fibers on the opposite end. And that instead of being arranged in these discrete three main categories, there is a transition from slow twitch towards faster and faster twitch fibers as you go along there. And that, I'm not a physiologist, so I can't say this for sure, but my thought process on that is that we know that fibers will transition from one type to another. So with a lot of endurance training, the fast twitch A fibers, those ones that are sort of in the middle there in terms of they have some oxidative capabilities. They can run on, they can oxidize glucose to be used for fuel. But they have higher force than the slow twitch fibers. And athletes that do a lot of endurance training, those fast twitch A fibers begin to look more and more like slow twitch fibers. They begin to take on more and more endurance characteristics over time. And likewise, if you did a lot of sprint training, some of your fast twitch A fibers would start to look more and more like the fast twitch B, the sprint fibers. And there have been a number of studies, especially on rodents, that show they've done these longitudinal studies that have rats running on a treadmill for hours at a time, and then they look at their fiber conversion or fiber transition, and they can see that the amount, if they do endurance training with these rats, the rats become more and more slow twitch dominant. The only human study I know of, and I'm sure there probably are newer ones done, but back in I think the 90s, the Finnish exercise physiologist Heikki Rusko did a study he took junior Finnish cross-country skiers and he tracked them through their career into adulthood, some of whom went on to perform at a high level, World Cup level. And what he saw was that as they aged, they became the same athlete because of the volume of endurance training they were doing, got more and more slow twitch dominant. And so I think not only happens in rats, it appears to happen in humans as well. So it makes intuitive sense I think when we're trying to create a model of this fiber, the fiber makeup in the muscles, to not think of them as these very discrete categories, but instead of more of a continuum, that you're going to have some very weak, slow twitch fibers, and you're going to have, some very forceful, fast twitch fibers, and everything in between. So we talked, let me go back to that slide. Oops, I meant to go, sorry. Oop, there we go. We noticed that these, as we go up the scale, we ascend up the scale from the slow twitch to the fast twitch here, we see that the motor nerve becomes larger in cross section and the fibers become larger in cross section. And the higher the force the fiber, or the more fast twitch that fiber is, the more nervous energy it takes to fire it. So the way these muscle fibers are fired is that the signal starts in the brain, starts really in the motor cortex. And we have these motor nerves, you can see in the little drawing there, that run down and attach to muscle fibers. Those things that look like fingers there are bundles of muscle fibers. And the motor neuron and the muscle fibers that it attaches to are called motor units. And we know that, like, the faster twitch motor units have a higher activation energy, and we'll talk about that here in a second on another slide. And the slow twitch fibers, the smaller fibers, have a lower activation energy. But when we train, the brain gets good at recruiting certain motor units in certain patterns. So if we do repetitive movements like running, skiing, swimming, then the brain starts to hardwire in what's called motor patterns. And it gets really good at recruiting these motor patterns, these motor units, in just the right order, in just the right amount of force to create the desired outcome movement. And I think one of the ways to understand this is to look at a child that's learning to walk. Their central nervous system has not figured this out yet. But very quickly, through practice, they begin to, as the child learns to be able to walk, that first is the movement's all erratic and spastic, and they might fall down, and because the motor units are not firing in the right orders. But as they become skilled at walking, then it becomes smoother. Even by childhood, you're able to walk without thinking about it. But for them, when they're first learning, it's a big task, and it's like any complicated task we'll learn it the same way. Children learn much faster than adults because we tend to have already hardwired in a bunch of motor patterns, and we often have to unlearn wrong patterns in order to relearn correct patterns. But watching any high-level athlete perform a complicated sport, whether it's dunking a basketball, high jumping, sprinting, catching a football while you're upside down in the air with, let's say an NFL running back. I mean, those types of high-skilled movements require a tremendous amount of training to hardwire the system so that it fires those motor units in just the right order. And we need to practice those skills. Rock climbing is a great example of that, of a very complicated, I think it may be one of the most complicated sports because there are virtually an infinite number of movements. They're not always the same. Like, let's say a high jumper needs to just learn to do the high jump over and over again and do it really well. But a rock climber is going to need a whole lot of motor patterns in their motor pattern library so that when they encounter different movements that they've practiced those movements enough that they can be formed smoothly. The way this happens is with a process called myelination. And some of you might remember, did an article about that years ago. Maybe we should redo it, but it's back at Uphill Athletes still. And so myelin is a insulating factor that covers these motor units, or the motor neurons, so that they don't lose this. It's almost like having insulation on an electrical wire. The better that wire is insulated, the less leakage there's going to be, and the stronger the current will be at the other end.
Just to clarify the one point, because all the muscle cells themselves all have the same, I think it's called the gate threshold, to achieve an action potential, which is like minus, I think 50 or minus 55 millivolts. But it's actually the importance of things like sprint training or max power training is to actually, it's actually the effort to get the maximal contraction to activate those fast twitch B fibers is the only why. And then the importance of often what it could be like bouldering, but rest or with sprint training, why the rest period is as important, if not more important, than the actual efforts to achieve that full max power effort.
Yeah, the higher we'll talk a little bit about that later when we start talking about some of the zones, but the higher the force recruitment that you're trying to create, whether it's, hill sprints or, one-arm pull-ups or sprint training or bouldering, the more nervous energy it takes. And when you have a high, this energy that's required to fire these motor units so the muscles contract, it takes some time for those things to restore themselves and be able to produce maximum power again. And that's why the long rest between maximum efforts, whether it's max strength training or power training, sprint or speed training, because if you don't allow these motor units, which the higher the force motor unit, the worse its endurance. And so it doesn't recover very quickly, these fast twitch fibers or fast twitch motor units. And if they don't recover, then when you try to sprint the next time or do the max effort, those fibers are still too fatigued. They will not be fired by the cortex and motor cortex, and your force production will be lower. You won't be developing the other physical qualities that go along with producing high force. You have to be able to recruit them in order to train them. And so, when you are fatigued, so like this would be why, in a climbing, a hard workout for climbing, for instance, you would do the high power, high force stuff early in the workout and do the endurance training later in the workout, while those motor units are fresher, rather than trying to do the opposite. Because if you did a big endurance session, there's a good chance that when you tried to do the high power, that those motor units are already going to be fatigued and they'll need a long time to recover. So in the way the muscle fibers were recruited, as we mentioned earlier, is with what's called the size principle, so that the lowest force fibers or the slow twitch fibers are the first ones to be called in to do the work. And as more and more force is needed, the more forceful fibers, the faster twitch fibers, with they'll have thicker cross section, and the motor nerves are also thicker in cross section. They get called in. And then, we think, should I mention this part? That we think that means they need a stronger motor signal to drive those faster, higher force fibers. How you measure that, we're not exactly sure. And our little petty research hasn't been able to help us determine that. But I think it's a way to think of it takes more conscious effort to recruit those faster twitch fibers. So hopefully we haven't confused people too much with that little segue. So now we're going to begin to talk about the endurance component of the recruitment of these muscle fibers. And this is a very, qualitative view. This whole slideshow is mainly qualitative. We're not trying to put hard numbers to any of this stuff. We just want people to get the idea, the concept here. That in this little graph, we've shown what's missing along the horizontal scale would be intensity, and on the vertical scale would be lactate production, or it could be glycolytic metabolism is going to increase as the intensity of exercise goes up. So initially, when you start exercising, with an easy warm up, let's say blood lactate, you're just recruiting those slow twitch fibers. That's what the blue is there at the bottom that says ST fibers. You're probably mainly going to be, if you're well trained and well fat adapted, you're going to be almost primarily using fat for fuel. And often we see that initially lactates drop in the first few minutes of exercise at low intensity. The reason for that is the aerobic metabolism takes a while to fully come online and get to where it's producing a lot of energy. And then we reach a point where that we call the aerobic threshold, this blue vertical line here, or often first lactate threshold, first ventilatory threshold, has a number of different names. And here's when we begin to shift more into the using fat, and actually sugar glycolysis begins to dominate at this point. And as a consequence, there begins to be the first real rise in blood lactate. You could see that here, the slope of this lactate curve, these black dots, black dashes, begins to increase. And eventually intensity reaches a point where we're needing to start recruiting those fast twitch B fibers that are almost exclusively using glycolysis or glycolytic metabolism. And so the production of lactate goes up significantly once you cross this red line threshold. This would be called the anaerobic threshold, or the second lactate threshold, or the second ventilatory threshold. Like a lot of these physiological terms, there's a bunch of confusing names, but hopefully you can see how these relate. But here, lactate production increases very rapidly because of the dominance of these fast twitch fibers and their exclusive reliance on carbohydrate for fuel. But this is just to kind of give you a general idea of what happens as we begin to recruit more and more forceful fibers as we go up the intensity scale. And looking at this from a kind of a heart rate standpoint, we have another way of this is, maybe we'll be able to now start relating this to zones. Here we've got somebody who isn't particularly well trained aerobically. On the left-hand side of the screen here, you'll see that this is a low intensity. We've got heart rate across the bottom scale, and here the lactate that remember we mentioned that slow twitch fiber can take up and utilize lactate that's being produced by faster twitch fibers. Here you've got excess capacity for lactate removal or lactate use. It exceeds the production rate, and you can see once again lactate begins to drop, and then eventually it starts to climb. And this blue vertical line, the aerobic threshold, this first ventilatory or first lactate threshold, there's several different definitions that indicate where this line ought to be placed, but it can be thought of as the first measurable increase in blood lactate production. Some people would also call it where blood lactate production increases by 1 millimole per liter. And that's roughly what we've shown here. And then we're shifting into more fast twitch fibers, in faster twitch fibers here in this zone here. It's what we term zone 3. And here, roughly, lactate production or lactate removal is approximately equal to lactate production, especially right at this red line. This is the point where lactate production and lactate removal are equal, is this second threshold. And then above that, in what we would call zone 4 and 5, lactate begins to climb dramatically because the glycolytic process is happening so quickly that lactate is being produced faster than it can be removed and utilized. And so blood lactate begins to climb very quickly. So here we've gone from, here where we're just kind of generally looking at the metabolic processes that fuel these different intensities, to here where we start to equate that to heart rate, but still thinking about muscle fibers that are reacting or causing these different zones. Anything to add to this one, Leif?
I don't think so. I suppose just for some people out there, clarifying that even though we use anaerobic threshold as the as a term there for the second lactate turn point, of course, it's a bit of a misnomer in the sense that there is still slow twitch fibers involved in that pool, and there is oxidative metabolism still going on. So it's not truly anaerobic in that sense.
Right, but the glycolytic process that's fueling those faster twitch fibers is sort of outstripping the ability of those slow twitch fibers to take up the lactate. Yeah. That's the main point I think people should grasp from this slide. But this is for a person who would not, we've called them an aerobically deficient athlete. But if we go look at here where we have someone who's very well trained aerobically, we see essentially the same thing. We've got heart rate across the bottom, lactate production on the vertical scale. Here in zones 1 and 2, we notice that the aerobic threshold here has moved significantly to the right. In other words, so this person would be able to, let's say, run much faster at this aerobic threshold than the person who's not as well trained. Their aerobic threshold is much lower, both in terms of heart rate and almost undoubtedly in terms of speed. But what this says is that this person has more capacity in their aerobic system for producing energy, or ATP being the energy molecule. But and so this would be someone we would say has a big aerobic base or a high aerobic capacity, meaning that the aerobic threshold is moved quite far to the right. But the same thing would be true of the other zones, zone 3 and zone 4 and 5 above that threshold. It's the same thing, metabolic processes that are going on. It's just that this aerobic threshold has moved so far over here to the right. And it's kind of squeezed down the difference between the anaerobic and the aerobic threshold here has become much smaller. And for an elite athlete, this might only be 10 beats, 10 heart rate beats. We see that often with a very well-trained endurance athlete. So all zone systems need to be related to intensity, because that's the point of them, so you have a way to mark intensity. They should be easy to use and in real time, and that's what heart rate allows us to do, or power meters would allow us to do as well. So most of them will do that for us. Then ideally they're also grounded in physiology rather than in, let's say, a percentage of your maximum heart rate or something like that, which I think is that is a bad idea, to have your zone system based purely off of some formulaic formula that gives you a percentage as a percentage of maximum heart rate. So it should have some connection to your own personal physiology, and that could be done through lactate, heart rate, pace, muscle fiber recruitment, all of that. And by what we're really big fans of is identifying this point, this blue line, this vertical blue line, the aerobic threshold, and this vertical red line, the anaerobic threshold, for each athlete that we work with. Because when we have identified those, then these zones are now personalized or individualized to that athlete. Because if you don't do that, and you're just using some random, again, percentage of maximum heart rate or something like that for your zones, you don't really know if that is your personal physiological response to exercise. But if you do some testing, and very simple tests, we've written quite a bit about that, and we'll put a link to our favorite tests in the show notes here, so that you can click and read that article about the kind of testing that we do. They're very simple, they're free. and they will definitely help allow you to personalize your intensity zones. And this little chart can help you. It's very similar to the one that's in training for the uphill athlete, but I've expanded it just slightly. So we'll run through it really quickly, but basically what we're trying to do here, we've identified these. It's essentially only 4 zones that relate to heart rate, zones 1, 2, 3, and 4, because the recovery zone, which is very easy, heart rate's not really that useful for it. And then the zone 5, which is essentially a maximum effort, heart rate is not particularly useful there. So, even though we use a 4 heart rate zone system, and even though there are technically 6 zones, the recovery zone and the maximum zone, though heart rate doesn't play really a role for them. But in this chart, what we've tried to do is identify, describe what it should feel like, the description there on the top, what the heart rate is roughly, then, the sensation of the relative perceived exertion. Then we've also given blood lactate levels. Again, rough guidelines here. People are going to be slightly different from, person to person. And then what it should feel like in terms of your breathing. How hard is it to talk when you're doing this? And then also that other green vertical column, we talk about which muscle fibers are being recruited to do this work. And then what the training effect is, what you would use these zones for in that next column, and how you would train these zones in the training method. And finally, the duration of this type of training. So we're not going to go through every single one of these, but I think we're leaving this in here for people to use as a handy reference, because I think it can help people or relate all these things we've been talking about. What your perception is, what your heart rate is, the lactate level, breathing, the training effect, what's going on. And I think this can be handy for people to decipher what these zones do.
I guess one comment, if I could make, Scott, would be with the RPE, the subjectiveness of that in and of itself, and just for people to think about that it's a function of time and intensity. So if someone is doing a 4-hour run at zone 2, it's probably near the end going to feel pretty hard. So just thinking about the potential, like tailoring that to the individual.
Good point. Yeah, the longer the duration at any given intensity, the harder it's going to feel for sure. And maybe it warrants, we did talk a lot about this in the Zone 2 podcast and the Zone 2 article, but for the poorly trained, the low endurance, or let's say aerobically deficient athlete, training in Zone 2 or at the upper end of it at your aerobic threshold is going to feel quite a bit easier than what that same heart rate or that same lactate level, that same intensity will feel like to a well-trained athlete. And that's because the well-trained athlete, as remember back a couple of slides ago, the well-trained athlete, at their aerobic threshold, they are operating at a much higher speed and heart rate than this athlete who is aerobically deficient. Here, this one, may barely be able to run before lactate begins to rise and they hit their aerobic threshold. Whereas this well-trained athlete might be clipping along at a 6.5 minute mile pace here. And so even though they're both in a very similar metabolic state, this well-trained athlete is going to be working considerably harder than the aerobically deficient athlete. So what we're trying to get across here is that the intensity is directly related to the muscle fibers that are being recruited, so that whenever the athlete needs more force, the motor cortex responds by recruiting more units according to that size principle that we've talked about, and that the production of this energy molecule ATP is directly related to the fiber type. the ATP production from these faster twitch fibers is going to be coming, largely from glycolysis or breakdown of sugars. Whereas in the slow twitch fibers, a lot of it's also going to be coming from the breakdown of fats. And so this is why we can use lactate as also a proxy for or an indicator of intensity. But back to what we started off with, we're the easiest thing for most of us to use, especially on a daily basis in real time, is going to be heart rate. And here's another kind of illustration, very, again, quite qualitatively, but what we're showing here, and this is, we've got, intensity on the vertical scale, and then the fiber recruitment according to that sort of size principle that as the intensity is quite low over here on the left-hand side in this recovery zone, the force required is quite low. And so, but as the force increases, as we move to the right, the motor cortex is going to begin to increase, recruit more and more of the slow twitch fibers. And I've used this blue color here to try to indicate that, we're getting more and more fibers. These fibers, if we think of this as a continuum, these fibers over here, closer to the aerobic threshold, are probably more, according to this, or our continuum idea that we're a fan of, that these fibers are probably slightly more forceful than these fibers over here on the very left-hand edge in the green. So the force is increasing up to this, our aerobic threshold, this blue line. And then when we get into these fibers here in the middle, we're beginning to recruit, more and more faster twitch fibers, more and more forceful fibers, and then transitioning into the highest force fibers here. And the black line indicates, similar to what we've been talking about, indicates the lactate as it rises, as these more forceful fibers begin to get recruited. So now we'll talk in each individual zone. So what these, real briefly run through these as what they are, what they do, and why we would not want to, why we want to be aware of what we're doing when we're training in these zones. So this recovery zone, it can be everything from, an evening walk with your dog around the block to, for some people who are very well trained, maybe it's going to be, an hour and a half, very easy run. But it needs to be, it's not designed to increase your fitness. It's not really stressing the metabolic system. It's just trying to speed recovery and get you ready to get back to training as quickly as possible. And I don't really think it's very valuable to try to pin it down with heart rate. I like to think of as the way of doing this is you should feel better after one of these workouts, or at least within a few hours of having done one of these workouts, you should actually feel better than when you started it. So the famed running coach Renato Canova he calls this type of training stumblingly slow. Now, for some of his world-class runners, stumblingly slow might be, a 6-minute mile. So you have to take that into consideration. It's all relative. What's stumblingly slow for, a 2:05 marathoner would probably be, faster than many of us can run full out. But what it means is this is extremely easy training relative for every athlete.
Yeah, and perhaps I would just point out that I think, I've seen this a fair bit personally, that recovery work is extremely relative. And if your normal, like long run is, say, a couple hours, and if you're doing an hour and a half, you can't really call that recovery. So it's all relative to what your training volume load is to begin with, and not to trick yourself and think you're doing a recovery zone when you're actually just doing a workout.
For sure. Yeah. I mean, I think for a lot of people, it'll be a yoga session. Could be just, lying on your living room floor and stretching or foam rolling. It could be an easy swim in a pool. Could be, hopping on a stationary bike for 30 minutes just to get your blood moving again. any tool that you have that increases your speeds up your recovery and gets you back to the ability to start absorbing harder training again, that would be categorized as recovery work. And that's why, once again, trying to put it in terms of heart rate is, I think, a little bit unnecessary. So here in zone one, referring back to that green chart, this is where we would be building aerobic base training for long days, or this is something you might do on a day when you're a little bit tired. It's also the kind of aerobic training that very well-trained athletes will do predominantly. They won't do quite as much zone two because of what we just talked about, that zone two can tend to be pretty fast for them and fairly demanding. If you're well trained, this will be predominantly using fat for fuel. Blood lactate's at a pretty low level. It should feel quite easy, and you should be able to, carry on a conversation with your running partner. And depending again on your personal training volume, probably minimum duration of something like this to be very useful would be something in the range of 30 minutes. But for a well-trained athlete, this could be several hours of work too. So this is the one that gets all the attention. As I mentioned, we did a pretty extensive podcast and article on zone 2 training. It's listed at the bottom there. That's the podcast number 63. So this is the zone where you probably maximally build that aerobic capacity. This is a thing. Training in this zone will move that aerobic threshold to the right. Obviously, it can't continue to do it forever, but for people who are aerobically deficient, this is one of the places we can see the biggest gains in their work capacity aerobically, training this so to move that aerobic threshold to the right so they can run faster, do more work, and still be aerobic. Pretty much maxes out the slow twitch fibers in terms of the bundle of fibers that you're recruiting. This would be like the aerobic threshold is really kind of a marathon pace for most people. And at the top of it, that aerobic threshold, this would be like about roughly 50-50 fat to carbohydrates. Lactates will run in that range, are 1.5 to 2.5. But this is both these zone 1 and zone 2, the biggest stimulus to improving aerobic capacity is the volume or the duration. So, more of this will almost always produce better results. By almost, what I mean is until it doesn't produce better results. You can overdo this training just as well as you can overdo high intensity training. So if you're not, let's say, this would be the reason you wouldn't just jump into an elite level running program that was, had 100 miles a week, because even though that would have a big aerobic training stimulus, if you're not accustomed to that kind of training volume, two things would happen. One is you'd probably become overtrained, and the second, you would probably become injured. So even though volume is the key, you need to, be sensible about it. You're not just going to dive into a massive volume of this kind of thing. And as we mentioned earlier, the perceived exertion for this can be ridiculously easy feeling for someone with aerobic deficiency syndrome. They may even have to walk to stay below their aerobic threshold, to stay in zone 2. Whereas somebody who's well trained, like I said before, they might be, running at a 6.5 minute mile, something like that. So it's going to be considerably faster for them, and their perception of it will be more moderate. You usually can carry on, a bit of a conversation with this. You might have a slight loss of breath and be able to speak in shorter sentences. And similar to the zone 1, it's going to be, a duration of 30 minutes to a few hours. Anything I'm leaving out on that, Leif?
No, I think that covers pretty much everything. I guess one thing that comes to mind somewhat in relation to this is establishing your zones specific to the activity that you're doing. This makes me think of in the context of, you know, I suppose where pace decouples from heart rate a little bit. So if you go from like a marathon training plan to mountain running, for example, you know, your local like muscular facilities will become much more important depending on the modality you're choosing, right? So just being specific about how you're also establishing your zones with these.
Yeah, I think, well, especially if you're changing sports, like ski, you know, let's say you're doing ski touring all winter and you're switching to a running program in
Yeah.
the spring, or you get injured, you're a runner who becomes injured and you need to get on a bicycle for a month or so to heal whatever this injury is. You don't want to just assume that your aerobic threshold is the same across all these sports. In all, especially when you change from something that's weight bearing, like running, to something that's non-weight bearing, like cycling, the aerobic threshold is going to be dramatically different. And so you would want to retest aerobic threshold when you make, especially make a big change like that to non-weight bearing.
Yeah.
In fact, someone wrote in recently on the forum about how they had mistakenly tried to use their running aerobic threshold training when they became injured and started training on the bike, and they quickly became overtrained
Because
because
they just cook their legs.
they cooked their legs. Yeah, the intensity was way too much when they weren't well trained on a bicycle.
Yeah. Yeah, and I mean it's the same I think we see with the running and transitioning to like something like ski mountaineering. It's similar, but it is different.
Yeah, but especially when you've got, fairly, well, even lightweight ski gear is going to be a lot lighter than a pair of running shoes. So, they just have the added muscular component that will make your heart rate, the difference between the stress on the muscles and your heart rate will be quite different in all these different sports. So, yeah, don't just casually, jump from one sport to the next without reestablishing these zones, especially this one. I think this is probably the most important one to really nail down. So this next zone we're going to talk about is zone 3, and there's something really important happens here. And that is that I'm going to move this so I can see and put it over that our little girlfriend there was bent over gasping for air. Maybe I'll put it in the middle, put us in the middle there. Okay. Anyway, as the intensity increases, and now we reach into that, we're above the aerobic threshold, we get into this zone 3. Now glycolysis or sugar metabolism begins to play a bigger and bigger role. And as a consequence, we have this red arrow, lactate production has beginning to increase quite a bit. So the glycolysis is taking place up here where my cursor is. That's producing some energy, the ATP molecule that goes to be used in these running muscles to help propel the runner. And we've got glucose is this primary fuel right now in this type of metabolism because we are above the aerobic threshold. And along with glycolysis, we will begin to see a rise in lactate. And we have this metabolic fork in the road that I'm using as this sort of metaphor for what's happening, or analogy here, is that if you are aerobically deficient, this lactate basically has nowhere to go, and it begins to accumulate, which will in the end have the result of you becoming more and more fatigued, like this little person over here on the left. The aerobically fit person can take that lactate that's being produced, can shuttle it into mitochondria. And I've got down below here, this is, this goes into the mitochondria of these slow twitch muscle fibers of people with a big aerobic base. That's that graph we showed earlier where the aerobic threshold was moved far to the right. And then this mitochondria can take that lactate, use it as fuel, and produce a whole bunch of energy, this ATP molecule, much more than comes out of glycolysis because it goes through the oxidative process here in the mitochondria. And so the outcome is a lot of energy that then goes into the running muscles for this person. So This is why you want to have that big aerobic base, is why it's the most important quality for all endurance athletes to establish. The first thing, and if you don't move that aerobic threshold up as high as you can get it, you're always going to be limited, and you're going to end up with more and more lactate accumulated, and which the end result will be that you'll fatigue more easily at the same pace that this other athlete could maintain. This well aerobically trained athlete could maintain that same pace for much longer.
I guess, yeah, perhaps, yeah, one thing it makes me think of as well is just along with the lactate, having the hydrogen ions also accumulating, which lower the pH and ultimately start to inhibit the muscular contractions, which is a little bit more in the weeds, but perhaps, I think some people might find that interesting and may have heard of that, just particularly with the products out there now, like the bicarb available and whatnot with the Morton, just to have a bit of context onto why those exist.
Yeah, there's a lot that's going on this in this process right here, this glycolysis and the lactate production. We've left out the whole step with pyruvate on purpose here. There's an intermediate product called pyruvate. So we're not making this a physiology class, but Leif is absolutely right. There will be an accumulation or an increase in acidity or a drop in the muscle pH that happens here that also seems to have, we don't know totally cause and effect, but there's a lot of theories about how this works. But definitely, the increase in lactate goes along with a lowering of the muscle pH, which goes along with lowering muscle force output. So all those are bad things. So the more we can be aerobically fit and have that big aerobic base, the more energy we can get out of this lactate, and the faster we'll be able to run for longer, which is indeed the whole goal of endurance training. All that last slide was what's happening in this zone 3. And now we're going to just talk a little more about, this is what's coming out of that chart. This is between the aerobic and anaerobic thresholds. Glucose or carbohydrates begin to dominate as the fuel. This is not really what we would call aerobic base training. But this has a pronounced effect on improving the endurance of those fibers that are used in this zone 3, those faster twitch, what we call the fast twitch A fibers. You're still going to be able to speak. This will not be, feel hard. It's going to feel kind of like fun hard. You'll be able to have, carry on a conversation in short sentences in this. The lactate for people, those that will be using it, somewhere in this 2 to 4 millimole per liter range. From this type of training, you should be able to recover within 24 hours. And we haven't done a podcast on this, Leif. Maybe you and I can do it some other time, talking about this whole concept of double threshold workouts. We've seen a lot of benefit with high level athletes, and they are able to recover within a few hours. But you should, even if you're relatively new to this type of training, if you don't recover within 24 or so hours of this type of training, you were probably going too hard, or you did too much volume of it for your, to get started. Now we're up into what would be really considered high intensity training, up into zone 4, where you've recruited pretty much all the slow twitch fibers that you can pull into this game, most of the fast twitch A fibers probably, and you're beginning to recruit a lot of the highest force fibers now. The way this is going to feel is, you're just only going to be able to speak a few words, breathing very heavy, very deep breathing, rapid breathing. Blood lactate's going to be in that 4 to 6 millimole range. This will feel hard, but you should be able to sustain it for, several minutes without collapsing. And we'll talk about that here in another couple of bullet points, but this should not be maximum effort. This is, I think, a mistake that's often done when people are trying to train in zone 4, is they train to complete exhaustion in this. And that's what we would call zone 5, which we'll get to here in a minute. Almost always, this is going to be trained using intervals. And, this could be everything from, 30 minutes of 30 seconds on, 30 seconds off to, 4 to 5 times 3 to 5 minutes, usually with the equal rest. The most important thing about this is you need to rest enough that your speed can stay high and your heart rate can stay high the whole time. If you find yourself in a zone 4 workout intervals, and the first couple of, let's say we're doing 4 by 5 minutes, using an example from that one line there. If you're doing 4 by 5 minutes and the first couple went okay, and then the third and the fourth and the fifth, you began to slow down and you couldn't reach the same heart rate again, then you've started too hard or you're doing too high of a volume of this. You're not prepared for it. The thing that makes people slow down when they do this is local muscular fatigue. And since the heart is essentially a slave to the muscles, it's responding, then once the muscles can no longer sustain a high output and they're not producing, you're not running as fast, then the heart doesn't need to supply them with those muscles with as much oxygen. So the heart rate will begin to drop. So that's one of the sure signs that you don't have enough local muscular endurance to handle this type of training, is that you begin to slow down during your interval workout, and heart rate begins to drop. And I think this is a very important training zone for a lot of athletes, but I think it's often overused and misunderstood. And we see people, they want to do the 5 by 3 minutes or 4 by 5 minutes, whatever, something in that range. They want to do that workout because they've heard it's very good for doing all kinds of beneficial training effect, but they end up grinding through it and just getting slower and slower as it goes on, heart rate dropping, and they end up exhausted at the end. And so they're not really getting the benefits that can come from doing this properly.
Perhaps I would just point out for any individuals who might be using a lactate meter as well, because I think it's maybe worth mentioning, is it's critical that you establish your own lactate turn point, that LT2, because the number will be different. It's not going to be fixed. So everyone will have a slightly specific like anaerobic threshold. And that's really important to note that, I think.
Yeah, it is. I mean, and probably a small percentage of the people that are going to be listening to this will be using a lactate meter, but that's a really good point. But that's why I think going on this perception, or can you complete, let's say, I'm going to give an example of a track workout because that's, it's easy to monitor there. Let's say you were going to the track and you were going to be doing 4 times 1 mile. And after the first 2 mile repetitions, you begin to get slower and slower and slower in each one of those, and your heart rate began to drop. Then you'd know that I'm not ready for this. I started too fast. Running too hard, and probably what you would be seeing is lactate would be not in that range. We don't want lactate going through the ceiling on this kind of training. That's not the point of it. It's the duration, a high volume of this kind of training is what's beneficial. But if you're moving very slowly and working really hard and your heart rate's low, you're not getting the benefit. I think that's the point I really want to drive home, because I just see way too many people misunderstanding zone 4 and overusing it, or misusing it, I should say. Okay, lastly, we want to jump into zone 5 here. As we mentioned earlier, heart rate just doesn't apply. This is going to be, as hard as you can go for as long as whatever the duration is. And we'll talk about those durations here in a second. I mean, these are going to be these are tough. You're going to be gasping for air. Lactates are going to be quite high. These will typically be quite short repetitions, and they will need to have a long rest in between them. So, for us, we use this type of training for developing power, like our hill sprint workout. This is a very common way to develop a lot of power. And like we use this a lot almost all year long with many of the athletes we train. And you can also go up into the 30 to 45 seconds where you're going to be developing anaerobic endurance using that. But for most of the sports we work with, this has very little application. Now, as for hard rock climbing and bouldering, this is a very useful type of training for that sort of sport, or for short other endurance events. But for events lasting in the range of more than an hour or two, this plays such a tiny role in energy production, and it's so exhausting that in the recovery can impact your recovery from your overall training. Might mean you'd have to reduce your aerobic training volume significantly to handle one of these workouts a week. So and I think if you look at training for the uphill athlete, comments by Killian, he mentions that he might only do 1 or 2 of these kind of workouts in a year. It's just not particularly valuable, but we wanted to show, what this zone 5 would actually look like. So what we've hoped to do is to give you some connection between, the cause, which is the underlying physiology of what's going on in the muscles, with the effect of, what you're seeing, both, heart rate, that sort of thing, or the effect of which would be your perception, but using things like heart rate and ventilation or lactate, which are proxies for this intensity. So we hope that, by going down in the weeds in terms of this muscle recruitment, it's made you hopefully more aware of these zones and what they're doing and why they're important for your endurance training. Any final words from you, Leif?
No, I think that's great, Scott. And yeah, thanks a lot for letting me join in.
Yeah, so Leif and I are going to be doing another podcast pretty soon, where we're going to dive into what we feel are the most important components when it comes to training for endurance. So hopefully we'll have that podcast out here in the next week or two. So stay tuned, and we look forward to seeing you on the next one. Thanks, Leif. Thanks for joining me.
Thanks, Scott.